Okay. Yeah, hi everybody, I'm Gage. I'm gonna piggyback off of some of the previous GIN and tracking talks and just kind of summarize here. In the edge classification paradigm, right, the idea is you have your set of tracker hits and you embed them as a graph by hypothesizing a set of edges that you'd ideally like to correspond to particle trajectories. So I just wanted to kind of break this down into 3 key steps. The first being where you build a graph. So you take your hits and embed them as a graph by assigning edges. In your second, you do GNN-based inference. So in the edge classification paradigm, you're assigning an edge weight to each of the edges. And then in the third step, you in some way recover the tracks, right? You might apply a threshold and just get rid of all the bad edges and take your disjoint subgraphs and call them all tracks. So I wanted to talk about a bit of an extension to this framework where, in a later stage, after you do edge classification, you preserve the edge weights. You don't get rid of edges, and instead you leverage them to do object condensation, which in brief is where you ask hits belonging to the same particle to condense in some learned clustering space. This is kind of the infographic we'll follow for the talk. So starting at the first step, graph construction. So I am retaining an edge classification portion of the graph neural network here. So we do need to build graphs initially. So I wanted to highlight some of the key features of the graph construction routine here. First and foremost, we're looking at the TrackML data set and in particular restricting just to the TrackML pixel detector. Also, I'm applying a few truth cuts here. A lot of the results shown are going to be kind of more in the proof of concept flavor. So, in particular, track PT, any tracks below 1 GeV are rejected from the graph. There are a few geometric constraints applied to whittle down the number of edges that make it into the graph. And then each event is broken into 64 sectors. So 8 and phi and 8 and eta. And I can kind of scroll through and you can see how the eta sectors are calculated uniformly. So you can see how the graph construction kind of varies as you change your eta region. And in particular, right, the purity of the graphs, which is the fraction of true edges, true particle trajectories that end up in the graph, it does increase as you move into the NCAP region. So our graph construction is better there. So if you look at an entire event, if you combine all the sectors in the events, you can just kind of get a feel for what each event looks like with these cuts, some of which are truth cuts imposed. We're talking maybe 10 to 14,000 nodes, order 100,000 edges, and then a purity of, roughly, we're seeing 15%, and then an efficiency, which is the number of true edges that have made it into your graph of essentially 100%. We're covering most of them. So with that said, that's the top portion of this infographic here. Our graphs have nodes, which are tracker hits. So they're embedded with features that are the spatial positions of the hits. And then edges are also given geometric features that correspond to the differences in the hits that they're connecting. And now we move into the graph neural network phase of things. So I first wanted to talk about the graph neural network architecture we're using. It's based on the interaction network, which is a message passing GNN layer. That was originally, it's physics motivated, applied to physics simulation. And the idea of the interaction network is that you have nodes in the graph, and the nodes are connected by an edge, which represents some sort of interaction. And you update the features of the graph in 2 stages. And the first stage, which is the edge block or the relational model, you take the node and the edge features and you use them to calculate the nature of the interaction. And then you propagate that interaction with a node block or the object model to re-embed your graph to come up with new node states. So that's just generally how an interaction network works. And we've studied its performance in the context of GNN tracking and shown that interaction networks do converge to good edge classification accuracies. So, okay, the edge classification step. So this is step 1 of the graph neural network itself. Given the input graph, you essentially optimize a binary cross-entropy loss and train the neural network to give you out some edge scores. So it's a number per edge, a number between 0 and 1. And instead of using that to reject edges, we simply append it to the edge feature vector to form a new graph embedding, this time with 5 edge features instead of 4. And that gets propagated downstream to the object condensation step. So what is object condensation in this context? The idea, as I said before, is to basically have hits that belong to the same track condensed in some sort of learned clustering space. And for the rest of this talk, I've taken it to be a two-dimensional clustering space. So it's H1 and H2 here are kind of the learned clustering coordinates. So for every node, every hit, you predict two quantities, which are first a condensation likelihood, which I'll explain in a minute, that's beta, and the learned clustering coordinates. And here there would be two of them. So for every one of the hits, you then predict that it's an unphysical charge. It's just kind of an auxiliary quantity called Qi. And the point of this is that you can facilitate object condensation learning at truth level. So the idea is at truth level, right, the maximum Qi hit belonging to a particle would become the condensation point for that particle, around which all of the other hits belonging to the particle would cluster. And you can see that here in the cartoon, right? I've kind of, you know, in this cartoon, maybe these central points are the condensation points for each object. And so the idea here is to optimize an attraction repulsion potential for each of the particles. So, you know, in the object condensation paper, basically the author recommends that instead of, you know, building a potential for every particle, you just take the condensation point in each particle, and then you apply the potentials. So the attraction potential is just a quadratic potential around the condensation point for the particle, and the repulsion potential is a hinge loss that ensures that any hit that doesn't belong to the particle that gets too close to the condensation point gets pushed away. Right, so here's just to kind of highlight what we're actually doing. There are three interaction networks used to facilitate the learning here. And you know, once you've re-embedded the graph 3 times with these interaction network modules, you then take the coordinates that you've learned and you pass them through some MLPs to get beta, the condensation likelihood, and H, the learned clustering space coordinates. And you can see here, just as an example, the attraction, repulsion, loss curve, and the train and test loss converging for various choices of hyperparameters. So, okay, what do you get? Like at the output, you run your GNN. You know, what you end up looking at is, okay, I've got a clustering space and I've got all of my hits re-embedded in the clustering space, but you don't have cluster labels yet. So this is kind of step 3 in the process. There are a number of ways to get the cluster labels. The author of the condensation, object condensation paper proposes one method, but here we've actually stuck to dbScan, which is density-based spatial clustering. And yeah, essentially, you know, you can, dbScan has a few tunable parameters. So per graph sector, you can kind of turn the knobs and you can get reasonable performance with dbScan. So, you know, at the end of the day, you run dbScan and it draws some cluster circles around your hits, and then you've got it. That should be your collection of tracks. So just to show an example of how this might work, I've written down a few different tracking efficiency definitions just to compare. The first being perfect matches, where you've got every hit necessary to generated by a particle inside of a cluster and no other hits. Or, you know, there's the double majority, where you've got over 50% of the hits in a cluster belong to one particle, and that, you know, those hits represent over half of that particle's hits. And then also this LHC loose match, which is the fraction of clusters that have just over 75% the same particles hits in them. Okay, so some results to look at. This is just for a single track ML event with the truth cuts I've described. Basically, so this is 4 different sectors from that event, where in the left subplot of each of these, this is the learned clustering space outputted by the GNN, and then the color is generated by dbScan. And then, so in the rightmost subplot, I've plotted it in cylindrical RZ space just to show that, you know, it looks like tracks if you go back to real space. And as I mentioned before, in the end caps, we actually constructed the graphs with quite high purity already. So in this example, it actually got all of the tracks right in the end caps. But of course, as you go more towards the eta 0 regions, it does start to make some mistakes as things get more complicated. This is an example from another event where you can draw more or less the same conclusions. So, okay, if you just kind of repeat this exercise for a bunch of different graphs, you can get like a per graph summary of, I guess this is 10 to 4 graphs. So we're talking, you know, perfect matches, maybe 83%, and then double majority 93%, and LHC was 89%. And then you can break that down per sector too, which is kind of where the interesting behavior comes in, where you notice in the higher ADA regions, the performance is much better than in the lower ADA regions, which I would tie back to the graph construction, which is much less pure when closer to theta 0. Okay, so right, just to conclude, GNN-based tracking usually occurs in 3 stages: graph construction, GNN inference, and then post-processing. So this is just a further enumeration of that kind of pipeline, where in this case, we've applied object condensation at the last stage to try and make better clustering predictions at output. So there are a number of directions we can move in with this. In particular, the object condensation framework has built in a way to do predictions of the properties of the objects that you are trying to build. So in this case, you might try track parameters, where essentially you append another multi-layer perceptron onto your network, and it learns to predict the track parameters from the condensation point representing each track. So that's one future direction we could run in. Of course, improving the graph construction in the central barrel region should boost the performance a bit, and at least help it be more uniform. And then, also you might wonder, why do we have this edge classification step at all? Why can't you just take the set of track hits and then throw them into the architecture and skip the edge classification? In fact, you can. You might imagine using GraphNet or a similar graph neural network that involves dynamic graph construction, where you're building edges and discarding them in real time. So that's another route you could go in here. And with that, I'll conclude. Thank you.
Great. Thank you so much. Any questions from the room?
Marcus, you said in the end caps, I didn't quite understand the reasoning you were giving why it's working better. I mean, one obvious thing is that, of course, you put more hits, no? And then in the barrel, right? I mean, so that helps the clustering, no?
Yeah.
And to take the right decisions. I mean, it might be that if you start extending it into the silicon, and you use also more information in the barrel, that recover some of the end cut performance.
Yeah, that very well could be. I imagine all of these effects are kind of correlated in one way or another. Yeah, the specific reason I was highlighting is just, the graph construction itself suffers, but right.
Yeah,
for sure.
Another question?
H, thank you. Great to see the talk, the similar talk now in person after you gave it at the IPA, so good.
Yeah.
One thing I was always wondering, and Sabrina and I tried once to do that, and I wanted to get your insight on that. Since you deploy a clustering at the end, a standard clustering, which we on a set of hits, is actually not incorporating all the knowledge we have. Yeah, because the moment you have 1 or 2 or 3 hits, you should be in a whatever clustering algorithm you use, you should be able to redefine what you take as a distance measure. Yeah, like you could either do this by, I think, metric learning to change the space, or, and this is an idea I once wanted to implement, never got to that you actually change the clustering algorithm, that when the cluster grows, you change what the distance to the next hit means depending on how your cluster looks like.
Yeah, I think so to some extent, like the metric learning aspect is captured here, right? Where
that's what you kind of
right, because this output space H is totally learned. There's nothing imposed on it a priori. We can get like a good slide to talk about it. Yeah. So another way you can make it more dynamic too is just as it's built into the object condensation framework. You can do the clustering also by just looking at the aphysical charge I described and applying a threshold to it, and that gives you your number of condensation points, which is the proxy for your number of particles. And you can just kind of do like distance queries that way, but it's not necessarily changing the metric, as you're saying. It's just like, this is a learned metric.
Yeah, but isn't the problem if you do a globally learned metric, it has to be the same sort of metric space for every event. While if you basically update the clustering, it's actually depending on the track. Yeah. So by having 2-3 hits together, which you already defined as a seed of the cluster, you change the metric by that. You adapt yourself not to a globally learned metric, but to a local metric. And I think that could give you a stronger, an even stronger performance increase.
Yeah, that's interesting.
Other question?
Maybe this is kind of on the track of what you're thinking, but does your object condensation use message passing steps, or is it like it does, right?
Yeah.
Okay.
Yeah.
I mean, in that sense, then it's using the features of the track to update the embedding space, right? So this is more sophisticated than just embedding all the hits into the space.
Yeah.
Right. Yeah, I can even take that a step further. Yeah, it's at every step. The way I've got it configured right now, you re-embed the graph with a message passing layer, and then you do it, in this case, 3 times. And I take each graph embedding and concatenate them all, and then use it to produce the update. So yeah, in that way, it might be doing.
You might capture that already, then yeah.
Yeah, it's reasonable to guess that. Yeah.
Okay. If there aren't any other questions, let's thank Gage again.